An increasingly common way to analyze data now is to run the data through cluster analysis or dimension reduction analysis. Cluster analysis is also known as hierarchical cluster analysis or HCA, while dimension reduction is more commonly known as principal component analysis or PCA. Now we are presented with data with large dimensions or large numbers of columns. And we can analyze these higher dimensional or high dimension data using these analysis or algorithms simultaneously to reduce the number of parameters or columns to lower number of parameters or columns. For example, column A, B, and C can be reduced to just column A because of the correlation that exists between columns A, B, and C. And that is why the technique is also called dimension reduction, because we reduce the dimensions from 3 to 1. In the act of reducing the dimensions, we also be able to extract patterns from the data. The reduced factors or components can give insight on the underlying pattern of the data. Here are some useful online resources that we can use to start talking about hierarchical cluster analysis. I like these resources because it uses R to explain the concepts of the analysis. The first one comes from an R blogger's website, and it uses a data set within R to run the HCA. The second is from the RStudio website, and it's another variation of running HCA on a dataset within R. Let's start with the first link. I'll go to this website now. I'll just copy this, open my browser, paste it in the URL, and then go to the website. You can also just click on the link to go to the website instead of doing what I did just now. Okay, so let's go through this link. Here it says, hello everyone, in this post I will show you how to do hierarchical clustering in R. We will use the iris dataset. So this iris dataset is a dataset that's within R. You don't have to import it. It's built in R, just meant to test analysis. So this tutorial doesn't teach you how to import data into R. Now, what is hierarchical clustering? If you recall from the post about k-means clustering, which you also have studied in the swirl lesson, it requires us to specify the number of clusters and finding the optimal number of clusters. So in k-means clustering, we define the number of clusters before we run the analysis, but for hierarchical clustering, we leave it open to the algorithm to come up with the appropriate number of clusters. Hierarchical clustering is an alternative approach which builds a hierarchy from the bottom up and doesn't require us to specify the number of clusters beforehand, and this is just exactly how I explained it. The algorithm works as follows. We put each data point in its own cluster. So each data point is a row observation, and then we identify the closest two clusters and then combine them into one cluster. Repeat the above steps. Still, all the data points are in a single cluster. And this might have been alluded to or have been discussed in the swirl lesson. Okay, once this is done, it is usually represented by a dendrogram-like structure. So a dendrogram is a branch and main branch and smaller branch clusters in the form of a diagram. So there are a few ways to determine how close two clusters are. These are some of the methods that we can use. There's a complete linkage clustering. We find the maximum possible distance between points belonging to two different clusters. That means it will not link the two clusters unless they are at the maximum possible distance. And then there's a single linkage clustering where we find the minimum possible distance between points belonging to two different clusters. And the third is the mean linkage clustering. Find all possible pairwise distances for points belonging to two different clusters and then calculate the average. And then there's also the centroid linkage clustering, where we find the centroid of each cluster and calculate the distance between centroids of two clusters. Now the complete linkage and mean linkage clustering are the ones used most often. This one, complete linkage clustering, and the other one is mean linkage clustering. So let's start doing this in R. So we are using the iris dataset, and in this dataset is about the 3 different species of flowers. So it's a dataset that contains information about different species of flowers. See whether we are able to cluster the data into those different species, because different species of flowers have different characteristics. So let us see how well the hierarchical clustering and algorithm can do to separate the data into the different species. We can use hclust, which is a function in R for this. hclust requires us to provide the data in the form of a distance matrix. So we have to first change from whatever format it was before to the matrix format. You can do this by using the dist function. By default, the complete linkage method is used. So this is the command, and this is the plot. So basically, hierarchical clustering is all about that. Let us try this in R. Let me go into R. First, we need to invoke or add the dataset into our environment here. So we can do that by just typing data and typing the name of the data, iris. Once you do that, then you see the dataset there in our environment, and we're able to use this data for our analysis. Now, what's the next line? The next line is actually converting this iris dataset into this dist, into the matrix format using this dist function. Right now, let's try to explore what iris is about. So let me just type iris here. And before there was not this information, and now we see there's 150 observations, which means there are 150 rows with 5 variables. We click on this and we'll be able to see the data itself. So here we see sepal length, sepal width, petal length, and petal width, and the species is setosa. So this is a type of flower. And as you scroll down, you can see these are the other types of the other species in the dataset, the versicolor with these characteristics, and the next is the last one is the virginica flower species with these parameters. So logically, you can think that different species will have different characteristics. So and you hope that by running this hierarchical clustering, we'll be able to break up the data into these different species, and then when it does that, like say group it into those proper groups, that means that the algorithm works to separate this species according to all these features or all these parameters here. Okay, so let's go back to the code so we see what the data is about. And let's see what happens if you were to just run dist. Okay, this part here, it says iris tree 4. What does that mean? So let me just type that out. Iris, which is the data frame, and then comma, this is the first part here is a row, and while this part is C, tree, and 4. What does that mean? It means that we want to see all rows because we didn't specify a number here, but we just want to see columns 3 and 4. So what are columns 3 and 4? So this is column 1, 2, 3, 4. Oh no, 3 to 4. Not 3 and 4, 3 to 4. So that means columns 3 to 4. So let's press enter, and we see that these are columns 3 and 4. So if you want to see columns 1 and 2, this is the same thing, but you can just type 1, 2. So basically what this line does is that it uses this function, and it changes this iris 3 and 4 columns into the matrix format. Okay, so actually here it can be a bit confusing because there's so many things going on in the same line. So see, we saw what this is. This is actually the iris dataset of 5 columns, but we just want the third and the fourth column. And then this one is to apply this on this 3 and 4 column dataset. So let me just copy this. I'm going to type it here and see what happens. Just clear the screen, close this, okay, and then type dist iris, comma C. Is it C there? No, just 3 to 4. 3 to 4. See what happens here? It changes it into the matrix format. And then it actually, let's see. Okay, we can see that it calculates this, but let me explain what went on to go into this. Let us plot dist. Sorry, not dist, but iris. The third column is petal length, and then iris petal width. I think this is the third and fourth column, petal length and petal width. So let's plot that and see what happens. This is the plot between petal length and petal width. So recall that in cluster analysis is all about finding the distance between points. So once we plot this, you see clearly you can see these two groups, one here and the other one here. And if you run the hierarchical clustering, if you run an algorithm that can separate it into groups, then you would expect that you'll be able to successfully separate it into these two groups, like how you can separate it on your own. So how cluster analysis works is that it chooses randomly from all these points a single point, let's say somewhere like, say, this point here. This is by random. And then it calculates the distance between this point to the nearest point. And then it calculates the distance from this point to this point. And then it calculates this point to this point here. So it calculates for every one of this. So it starts with this, then it goes to this point randomly again. It calculates the distance from here to here, calculates from here to here. So these, the algorithm, this dist, D-I-S-T function, actually calculates the distance from each point to every other point. And that distance is put into the matrix, and that's the matrix that we saw just now. Let me show it up. This is the matrix. These are all the distances between the points. Okay. And then we use HClass to run cluster analysis, or HCA. So it might be surprising to you to think that such a fancy name analysis just requires one line of code to run the analysis. Yes, in R, it's all of the analysis itself doesn't take that much time, but the preparation of the data takes time. So here, the preparation is actually the extraction of the columns that we want, then the calculation of the matrix for each of those values inside the data set that we want, and then running the cluster analysis. So this HClass clusters according to distance calculated using this function here. So let me just, and then the results you put it inside this cluster cluster variable. So let me just run this. I copy this, paste. If you run this, then it will give us the it doesn't show us the plot, but it just shows us the results of the analysis. It says the default method uses the complete method, and the distance is the Euclidean. Euclidean just simply means the distance between this point and that point using Pythagoras theorem. I think you know what Pythagoras theorem is, right? And there's 150 objects because there are 150 observations here. That's not really useful. We want to see the dendrogram. So to do that, we put it inside this variable that we haven't defined yet, and we put that function, the results of the function of HClass into that as yet to be defined variable clusters. So iris 3, 4. Then we see it's defined here. You can see the details inside here. And if we want to plot the dendrogram, you just use the plot function on the, it recognizes that this is a dendrogram, and it will plot the proper plot there. So this is the plot, the dendrogram, and like what I mentioned, when we look at the data between X and Y, we saw the two petal length and petal width, we saw the two groups. So is the algorithm able to separate the two groups? Yes, because you can clearly see that there are two groups here. Right? So it works well for that columns 3 and 4. Now let's go to the next step. So we see here, we can see from the figure that the best choices for total number of clusters are either 3 or 4. Oh, it's not really two groups. If you look at this group here, you see, if you want to look at the number of groups, you need to cut through the dendrogram. So over here, you can draw a line here, and that's where it becomes two groups, 1 and 2. If you put a line over here, then it becomes 1, 2, and 3 groups. And if you put it over here, then it'd be 1, 2, 3, and 4 groups. So if you cut it from here, somewhere closer to the top, then you have the two groups, and you cut it somewhere as you go below, then you have more and more groups. So this is quite subjective, and it really depends on the user and the case that you are analyzing. So according to the website, it's not that good yet because it's not able to, we don't want to cut it too far in the top, we want to cut it somewhere below because that one, it has to be somewhere in between. So here we're still not sure whether we can actually, it's still not clear whether it's just 3 groups or is it 4 groups. Okay, to do this we can cut off the tree at the desired number of clusters using cut tree. So let's just run this code, close this, like that. So this is a function, and we run it on the object here, clusters, and we want to cut it where it is at 3 groups, and we put the results inside cluster cut. Okay, and let us compare it with the original species. So this is how we study the performance of the algorithm. So let me paste there. So let me explain this function here. This code, it says we create a table of the iris species. This is, if you remember, if you look at the iris dataset, these are the species. So there's 3 species. So we spread it. We draw a table that has the species information, and we put the value of the cluster cut if it's at 3 groups. So let's look at the results. It says here that if we put it at 3 groups, so we are able to separate the setosa very well, because none of the versicolor and virginica is falsely identified as setosa. But between groups 2 and 3, we find that versicolor is 21 for groups 2, while virginica is 50. And for group number 3, we have versicolor all correctly identified, 0 was falsely identified as setosa and virginica. But group number 2 here is problematic because it's not able to correctly identify between versicolor and virginica, where it's close to 75%. Falsely, maybe it is a virginica group, but somehow some of the versicolor is still within this group here. So what we want actually is where one group will be able to explain, will be able to flag all of the actual species within that group. Like for example here and here, but not here. It looks like the algorithm successfully classified all the flowers of species setosa, like I mentioned, into cluster 1, and virginica into cluster 2, but had trouble with versicolor. If you look at the original plot showing the different species, you can understand why. So we did this plot just now, but we just did it in one color, so we're not able to specify which parts of the plot are the different species. So for this plot, we color code the point so that it represents a particular species. So here we see the plot between petal width and petal length shows that if it's setosa, it is clearly different in terms of petal width and petal length from the versicolor and virginica. And here we see that this is where it's a bit problematic for the case hierarchical algorithm to separate the two because the petal width and petal length variation between the two species are similar. Now let us see if we can better separate the data by using different linkage method. So the one we used before is the complete method. This time we will use the mean linkage method. So it's the same style except for there's an additional argument added into the dist function, and then we plot it. So let's try. So we copy this. Let me just copy one line by one line first. Paste this. Again, the difference between this this line here and this line here is the additional argument average, because the default is set at complete. So we run this, we overwritten the existing cluster, now it's written with the new analysis, and then we plot the clusters. Right, this is what we get. Okay, so here it seems to perform better, because if we were to cut it here, then we'll come upon that 3 groups, 1, 2, and 3, but still we're not able to judge whether it is able to classify according to species, because it's not written, the species there are not written here in the plot. By the way, these numbers here mean the number of the points. For example, this is number 25, this is number 17, in terms of sequence, like from top to bottom. Okay, so let's look at the explanation. Okay, so we can use that, we can see that the two best choices for number of clusters are either 3 or 5, like mentioned. If we cut it here, it's 3, and if we cut it here, it's 5. And let us use cut tree to bring it down to 3 clusters like before and see how it performs. So I'll copy, close this, cluster cut, and use the function cut tree, apply it on that clusters object and 3 clusters, and then we draw the table. So table, clusters, and we use the species column of the iris dataset so that we could separate it according to species. This is for the new analysis. What happened there? Oh, yeah, not clusters, it's clusters cut. Alright. So here you see that the complete method is able to differentiate between the species better, although there still overlaps. Setosa can be clearly separated. Versicolor seems to be working, but one of them still gets misrepresented as Virginicolor. For the third group, you see Virginica is 49 is an improvement, but still 5 of them is still categorized under versicolor. So there's an improvement, but not perfect. We can see that this time the algorithm did a much better job of clustering the data, only going wrong with 6 of the data points, this 1 and 5. We can plot it as follows to compare with the original data. So this is just the plotting, it's not exactly analysis. The analysis is just by applying the hclust function. So this is using, this particular plot is not the base plot, the one that you've learned. This is the ggplot, a popular graphics device in R. So this is an application of that. So let me just copy and paste this one and go through the code with you. Okay, so here, let me just control alt first, paste it, yes. So here it says ggplot, we run it on iris, and these are the aesthetics. These are the columns of the iris dataset. We have the petal length, petal width, and then the color, we separate the data based on the species inside. So let me just plot one by one. But there's going to be an error here because I didn't load it yet. So let me just load ggplot first, ggplot2. Okay, then only I can use it. Now, if you haven't installed ggplot, then you're not able to load it. So install packages ggplot2 first before you can use this function. So let me plot this. Again, we use the iris dataset. This is the iris dataset. And we want to plot the petal length column, the petal width, and then we want to group it based on the species. Okay, there's nothing shown here yet because we haven't actually plotted, we just created the canvas. So the next line is actually to add those points. So this line and then paste. This is to create the canvas and tells R which data set to use, which columns to use. And then here, this plus geom point is actually to plot the points. This is alpha is the transparency of the point. The size is the size of the point. So once I press enter here, then you get to see the points. Well, the transparency alpha is 0.4, that's why it's a bit transparent there. And the size is larger than usual because it's 3.5 times larger than usual, than the normal size. Okay, then we add in the geom point color cluster cut. I do it part by part so you'll be able to understand how ggplot works. Paste. Oh, don't forget the plus between. So we add another plot geom point where we put the color according to cluster cut, the 3 cuts that we've defined before. So this one would actually shows us the difference between the groups according to the 3 groups. So the previous plot is the red, green, and blue, and the plot now is, okay, the red is still there. But this black color inside the red points are the different groups. So you see here, these are the different groups. It seems to be, this is accurately separated because all of the red is denoted by the first group. If you look closely here, let me zoom in. If you look closely here, you see, okay, the green with the red is correct, but you also see some red with the blue. So this is falsely identified as a different species. This one seems to be working. The blue Virginica with the green, but this one is the green with the green. So this is again another falsely identified point. So this one actually shows you the ones that are not identified correctly. Now we go to the next line. This line here is just to annotate the graph. Paste. So plus, we scale color manual, values black, red, and green. So we want to use this colors only, black, red, and green, and we press enter. And here you clearly see that these points, this 1, 2, 3, 4 points, the one we can see are falsely identified as different species. So all the points where the inner color doesn't match the outer color are the ones which were clustered incorrectly. And that's the end of this article, or the end of this tutorial, or the video on this article. So I hope you'll be able to try it on your own or just follow along the next time you watch this video. Okay, that's it for this video. I hope to see you in the next one.